Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 5 Part C. Question 1 states, draw the block diagram for a cascade controller with inner loop process transfer function GV equals 1 over 0.1s plus 1. Inner loop proportional control gain of 1.2. Master loop FOPTD transfer function of GP equals 0.12 times e to the negative 5s over 12s plus 1, an outer PI controller with controller gain Kc and reset time of tau I equals 0.5. Find the controller gain to yield approximately 30 degrees of phase margin stability. So to start out with, we are going to draw our block diagram. So I'm going to start with the inner loop. And as usual, we're going to have a transfer function. That's our first block. And this was GV. And just like normal, before that you have your controller gain. And this will be GCI for inner. And you would have some stream going out, and then it would circle back around and be measured. In this case, we're going to assume that it's 1, but there would be an inner measurement. And this would come back around and be fed into something to compare it to. And then there we have our inner loop. Let me move this up for a little bit. Now for the outer loop, we still have a process going on, and that's our GP. So it's going on here, and it has a signal going out that way. So we have that going on. And then we would have some outer measurement device. Again, we'll assume that it's 1, but still there, so GMO for outer, and it would go all the way around this inner loop, where we would then see our controller for the outer loop, GCO, and then our set point would be put in on this side. Oops, I forgot our I did not size this out well at all. But we would also have our little compare here going in. And imagine we have our set point going in up there. Now we are ready to move on to the coding section of this question and determining the 30 degrees of phase margin stability. Here I just have this assignment pulled up, so I don't have to keep flipping back and forth on my tabs of what the functions look like. So the first thing we want to do is define our inner loop. So we're going to say that CV is equal to 1 over 0.1 times S plus 1. This. And then our inner controller gain is 1.2, which was given to us. Let's see, what should be G. And then our G inner is everything across the front multiplied together, so GV times GCI divided by 1 plus everything in the entire loop, so GV times GCI, since our measurement we are assuming is 1. Now for the outer, we have our GP, which is 0.12 times exponent negative 5s, yes, divided by 12s plus 1. And then for our outer device, this is where we'll see our step change. So this is 1 times 1 plus 1 over our tau I, which is 0.5, so 0.5 times S. There we go. All right, now what we want to do is make our Bode diagrams. So we're going to go through the same process that we went through in Part B. So first we want our omega values, and that was the log on the log scale. So we want to go from -3 to 0, and we want 500 steps. And then our g is going to be everything multiplied across just the one big function. So what we want is GCO times G inner times GP. I did realize we forgot something. We need to do G outer up here. And this is everything across the front, so GCO times G inner times GP divided by 1 plus everything in the loop, so just the same thing in this case, GCO times G inner times GP. Perfect. All right. Now here I'm going to go back over to the code that we just wrote in Part B, and I'm going to take our functions here that we wrote. This was just calculating, doing our substitution, identifying our real and imaginary parts, using those to solve for m, as well as phi, which is our angle. And then I'm going to steal our plotting as well. And again, this was just having two subplots, our x and y. For our first is our omega values and our magnitudes. Our x and y for our second diagram is our omegas and our phi values. And then for our top graph, we're on the log scale for both the x and y. And on our bottom one, we're on the log scale just for the x, and we're in degrees and a linear scale on our y-axis. Now we can use this to find our margin. And so to do this, we're going to do the reverse of what we did in Part B. We're going to start by looking at this top diagram with our m values, and we want to find at what omega value we're at one. So if we go over here, we'll find that we're at 1 at about 0.085. So now we can come down here and find that same x value. So we're looking for 0.085. So it's somewhere around here. And we're at about 160 degrees. And to get our margin of 30 degrees, we want to be at 150. So we are a little bit off. So to change this, we come up to our controllers. And I'm just going to lower this down to maybe 0.8 and see how that changes things. So again, we're coming up here and looking for a y value of 1, because that's when m is 1. And it's at about 0.076. So now we look for an x value of 0.076 on our diagram here. And now we can see that we are closer to 150, and we'll call it good in this case since we're just eyeballing the graph and we can't quite get exact value. Finally, we are going to move on to Part C, Question 2. This states, simulate the closed loop response of C1 to a unit step change in set point. So we can come over here to our code that we wrote in Part 1. To simulate the closed loop response, we can actually just take, again, from what we did before. So here is our time and y values using the simulation function, or the sim function. And instead of GCL this time, our closed loop response is really just that whole outer loop. So G outer. And then to graph it, we can again just take what we'd already written in part B and put it over here. And here we can see our response, where we can see the step change and then the system stabilize.